Woohoo. Okay, recording with the little camera. I'm recording with Zoom, even though we think it's not going to be useful. And is the little camera? Yes, it's going to focus very slowly. Is it? I hope so. Yeah, it looks like it's focused. Okay. So we're recording here. We start this. And right, okay, lots of stuff to do today. If you record with the view changed, how do I change the, so I go to speaker. At the moment, I don't see myself as speaker. I see somebody else. I see somebody else's name written. View, speaker view, that's what I've got. Top right, yes, but speaker view, it's on speaker view. Everybody sees me, but anyway, we have the little camera, fortunately. So let's just power through this. This is not one of the complicated, this is just to sort of pound in this, before we take any steps, our empty subsolution can be extended to an optimal solution. Suppose that after I steps, blah, 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 blah. This is just gonna drive that into your heads, okay? So, interval scheduling, this is sort of one of the classic introductory problems for greedy algorithms. You have some things, some activities. Maybe this is called activity scheduling in the book. Sometimes this kind of thing is called job scheduling, but job scheduling is a whole field. I'm just going to close the browser so it doesn't make beeping noises when people email me or something. Okay, so job scheduling is a whole field because normally, and lots of versions of job scheduling are really hard because normally you have an interval, or you have a start, a release time, and you have a deadline, and you can move the job around, and maybe you have multiple machines and blah, blah, blah. We don't worry about that. We just have some activities. They have start times. They have end times. And they all have equal profit, okay? So these are your activities. You can see these, right? Yes? Yep. Okay, so you have, each activity has a start time and an end time, and it has some profit. Well, it has, let's say it has profit 1. Okay, so everything is equally important to you. So this is going to be your day. You're planning your day, and you have a bunch of activities you want to do, and they can take different lengths of time, but you value them all equally. Okay, and you can't get the profit for one unless you do everything. Unless you do all of it. So if you decide to do this activity, it only counts if you do the whole activity. You start here and you do it there. And we imagine that you can't do more than one activity at a time. So you can't like eat lunch and watch the algorithms lecture at the same time. Obviously, in fact, you can, some of you probably are, but maybe you cannot meet a friend and watch the algorithms lecture at the same time, because if you're paying attention to the algorithms lecture, then your friend is going to be annoyed. And if you're talking to your friend, then you're actually you're wasting the time watching the algorithms lecture. Fortunately, it's recorded, so you can do it later. So algorithms doesn't really fit into this because you can watch algorithms whenever. So we want to select a subset of these activities. Okay, I'm not going to do that for all of them. And we want to select a subset. We want it to be as large as possible. We want to do as many activities as we can because we value them all equally. And so you're looking, why is Zoom is orange. Okay, now it's not orange anymore. And this is recording, right? Yeah. Okay, so how are we going to do this? So we can imagine these activities, we get them as a set or multiple, people are waiting to be let in. Admit all. Wow, there were a load of people waiting to be let in. I'm sorry about that. Okay, please mute yourselves. Sorry about this. It's, oh, yeah, okay. Please, if anybody sees there's somebody waiting to be let in, just like unmute yourself and let me know. Otherwise, please mute yourselves. Or I can just mute you. And I'll just mute you too. Okay. Is there somebody else? Okay, no. So how are we going to do this? So we imagine these as pairs, maybe. So this is time, and this direction doesn't mean anything. And so, for example, maybe this starts at, let's say, 6 a.m. and ends at 8 a.m. And this starts at 7 a.m. and ends at 9 a.m. And this starts at 8:30 and ends at 9, and so on and so on. Okay, so you really get this as a list of pairs. So it goes from 6 to 8 and 7 to 9, and they all have equal profit. And we want to take a scheduling element. Yeah, so these are intervals. Actually, okay, technically I shouldn't write it like that. Technically, I should write it like, let's imagine that these are half open, right? So that they're closed when they begin. It starts at 6, but then if it ends at 8, then you can start something else that starts exactly at 8. Okay, so you're super fast. You can get from one class to another, or from one activity to another in 0 time. This is the joy of being in a lockdown. Everything's online, so you don't actually have to run between buildings. You just like switch your Zoom meeting. Okay, how are we going to do this? So I said in the last class that usually with greedy algorithms, you sort on something. What we want to sort on. Has anybody seen these before these? Has anybody seen this? You have seen this problem before. Yeah. Okay. Have you seen the proof of correctness? I think, okay, not yet. Well, not from me, but okay. So you sort on the finish time. You might think, oh, what's the most urgent thing? What's the thing that's going to start first that I have to get ready for right now? But you don't do that. Where is my eraser? You sort by finish time. So let's say instead of 9, that just goes from 8 to 8:50, 8:30 to 8:50. So what we would do if you look at this, we say, oh, of these, what finishes earliest? It's going to be this one. So we're going to take this one. And then what finishes, well, actually, we could make this 9 o'clock because we would then look at, say, what finishes next? Well, it would be this one. Well, let's say this finishes at 9:10 to make this more interesting. 9:10. Let's say it finishes at 9:10. Well, we look at the one that finishes next. It's this one, but it overlaps this one. So we can't take both, and we've already taken this one. In greedy algorithms, we don't change our mind. So we take this one. We do not take this one. And then we look and we say, okay, this one, does it conflict? No, it doesn't. We look at the one that starts next, ends next. It's this, it doesn't conflict. We take it. The one that ends next is this one, but it conflicts with stuff we've already got, so we don't take it. What ends next? It's this one. Let's make this one start here. So that if we've been considering it by start time, we'd have looked at this one next and taken it, and we couldn't have taken this one. But we're doing it by finish time, so we take this one and not this one and not this one. And we do take this one, and so we can't, and then it looks like we can take this one. We cannot take this one. It looks like we can take this one. And then we cannot take this one, and we cannot take this one. Okay? So everybody sees what the algorithm is? Sort by finish time, and then process them in order of finish time, and take it if you can, if it doesn't conflict with something you've already taken. You can't take certain ones again. Oh, because you can't take this one because you've told, you've signed up, you're going to the gym between 6 and 8 because you're much more energetic than I am. So you've signed up for the gym between 6 and 8, you're going to the gym, so you cannot watch early morning cartoons or something, right? Between 7 and 9. So gym, no, so you've taken the gym, so you can't watch the cartoons. But then you can have breakfast. But then you cannot do whatever you do like between 8:30 and 11. I don't know. Then, so you took this one, so you couldn't take, you took this one, so you couldn't take these two. And you took this one, so you couldn't take this one, because you can only be doing one thing at once. You're maximizing the number of activities, yes. Sorry if you were one of the people who came in afterwards and I didn't let you in on time. Blame Zoom for lying to me, and then blame Microsoft for like producing such a crappy product that I have to use Zoom instead of Teams. Okay, so we understand the problem. We're maximizing the number of activities that we consider them all equal. And to do that, we sort by finish time and we process them and we take them if we can, if they don't conflict with something we've already taken. Why does this give us an optimal schedule? Well, before we've taken any steps, our empty sub-solution can be extended to an optimal solution. So we're processing it in order of finish time. And before we've processed anything, of the stuff we haven't considered, we can definitely take an optimal solution, right? Isn't this? No, this is easier than dynamic programming. I think you probably could. There are versions of job scheduling that you can solve through dynamic programming that you probably can't solve through greedy. But this version is sort of the typical thing for greedy. I think it's in Common License and Reisenstein. Okay, so before we do anything, we haven't messed up. Now, suppose that after I steps, we've taken, so we're, okay, ignoring this stuff. So imagine we haven't processed these. Oops, I erased one of the activities. Where was the activity I erased? Up there, right? Okay, so we're here after I steps. Yeah, let's say that I steps. So now we've processed up to here, and we haven't looked at the rest of them yet. So after I steps, assume that our sub-solution, the stuff in red, yes, 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 no, no, can be extended to an optimal solution. So that's true before we've taken any steps. Now, we have to show that after we take I plus one step, so we take this one. So our at this point, our solution can be extended to an optimal solution. And we're going to take this one. And we want to say, okay, if S does what we do, great, then our sub-solution after I plus one steps can be extended to an optimal solution, same S. But what if S does something different? What if S takes Oh, wait. Yeah, this one conflicts, so we couldn't take this one. So let's just mark that off because we want to consider the green one. Okay. So what if S takes this blue one? And we take the green one. Okay. So, so before, at this point, our subsolution could be extended to S, but now it can't because we take this and S takes that. Okay, now we do this exchange argument. We say, well, whatever S did after that, right? So it takes the blue, we take the green, and then we consider what the rest of S. It couldn't take anything else in here because it conflicts with what is taken. So we're going to call this the rest of S. Okay? So what if we take the rest of S and we say, now we're going to take S and we're just going to switch it. Instead of taking the blue, we take the green. Is that still compatible with the rest of S? Yes, it is, because if the rest of S didn't conflict with this blue stuff, then it doesn't conflict with the green stuff, with the green activity either, because the green activity ends earlier. So we can take sort of our stuff so far. So what we've done in I steps, and then S takes the blue one, and then it takes the rest of S. So it takes this, what we've done in I steps, it agrees with that. It takes the blue one, it takes the rest of S. We're going to take what we've done in I steps, and then we're going to take the green one, and then we're going to take the rest of S, and we're going to call that S prime. So this is going to be this activity plus the rest of S equals, well, okay, and also what we've done, so what we've done earlier, plus the green one plus the rest of S is, we're going to call this S prime. So S prime gets at least as many activities as S does, because it's the same as S on the red stuff. It differs only on the blue and the green, but this is worth 1, this is worth 1, so fine. And the rest of S, it gets the rest of S, because the rest of S can't conflict on the green. Okay, so we just swap the blue for the green and we get S prime. S prime gets at least as much stuff, and we're going to admit the person who's waiting. Yeah, sorry about having to stop and admit people. Okay, so sorry about, it's not a webinar, you can't just join. So the, and I will check to see what the clock says. 6 minutes. So, okay, so after I steps, we haven't messed up, then after I plus 1 steps, we haven't messed up. So by induction, we don't mess up. So the greedy algorithm, sorting by finished time, produces an optimal solution. So long as blue terminates after green. Yes, because we are if blue terminated before green, then we would have processed the blue first and we would have taken it. So this is, it's important that we're processing in order by finish time. Okay, good. So that's first thing we see with after, before we take any steps, our empty subsolution can be extended to an optimal solution. Suppose that after I steps, our subsolution could be extended to an optimal solution S. Then you do this exchange argument stuff, which you actually have to pay attention to what the problem is. And then you say, okay, and so after I+1 steps, our sub-solution can be extended to an optimal solution S prime. Therefore, by induction, the algorithm produces an optimal solution. Okay. So that's I think it's maybe not as interval scheduling, maybe it's activity scheduling. I forget. It's in CLRS. And it will someday be in the course notes when I get caught up. Okay. So the next thing, suppose we have some sequence of numbers 7, 2, 4, 3, 8, 1, 1, 2, 6, 9, 5, 8, 7, 4, 3. Okay. So we have some sequence of numbers, and we want to divide this. We want to partition it into the minimum number of, let's just say it's increasing. Okay, let's just, so I don't have to keep remembering to say non-decreasing. Can we partition this into the minimum number of increasing subsequences? So increasing means you can't have 7, 2, you can have 7, 9, right? So how are we going to do this? Well, you can sort of, well, I'm actually going to tell you this to save time because we have a load of stuff to get through. So what you do, you start, these are also called chains. So the increasing subsequences are called chains. So you start with 7. Okay, so 7 is the beginning of a chain. And then you look at 2 and you say, oh, well, I can't attach 2 to the same chain as 7 because then it's not increasing. So 2 is gonna have to be its own chain. And then 4, and you think, okay, well, I could either start a chain with 4, or I could attach it to 2. So I could start it, or I could attach it to 2. And then you have 3, and you think, oh, well, if I'd started a chain with 4, I could have attached 3 to 2. But now I can't attach 3 to 2. And so I'm going to have to start a new chain. Why do I put it below 2? Because I'm ignoring the 2 now, because I can't attach anything else to the 2. I can only attach it to the 4. So now I have a 1. I can't attach that to anything. So I start there. Now I have a 2. I can attach the 2 to the 1, or I can start its own chain. So I'm going to do that. Now I have a 6. I could attach 6 to the 2, or to the 3, or to the 4, or I could start its own chain. What do people want to do? 4. Okay. 9. What do people want to do? 7. Okay. Has somebody seen this before? Okay. 5. 7, 3. Okay, 3. Okay, 5, 3. 8. 8. Somebody says new. 8 says 6. 6. Okay, 6. Yes. 7. Okay. 7, 4. You always have to put it on the closest number if there are multiple options. Yes. So okay, it's not the closest. It's the predecessor, right? Because it has to be non-increasing. So if I had a 4 and there were a 4 here, I couldn't. If I wanted increasing subsequences, I couldn't put a 4 after a 4. What I do is I put it after the largest number, which is smaller. This is like, I don't know the Windows poker game. Okay, so we're just gonna do it. We're gonna say 4. And then the 3, I can't do anything. I have to start a new chain. So predecessor, yeah, predecessor and not equal, strict predecessor. And if there isn't a strict predecessor, you start a new chain. Okay, so this is saying that we have, what's the smallest number? Well, we have 7 and 9 are a sequence, and 2, 4, 6, 8 are a sequence. That's kind of cool. 2, 4, 6, and 8. And I didn't actually keep track of which 2s and 4s, but I guess it's these. And then 3, 5, 7. Okay. 3, 5, 7. 3, 5, 7. And now I've run out of colors. So it's going to have to be a red circle for 1, 2, and 4. And 4. And then it's going to be a green square for 3. Okay, so we have 1, 2, 3, 4, 5 increasing subsequences. I have to start the little camera. Okay, and we reset this. Reset, start. Okay, and then we take a drink of tea. Okay, so this is Superwitt's algorithm. Why is it correct? Well, before we take any steps, our empty sub-solution can be extended to an optimal solution. I feel kind of silly doing this, but I don't want you to forget. So look, if you get to the midterms or you get to a final and you're like, I have no idea how to do this question, but you think it's a greedy algorithm, then first, as I told you, sort by whatever you can think of. And at least write down, and this algorithm is correct because before we take any steps, our empty sub-solution, because then you get to the thing of like, and then after we assume that after I steps, we haven't made a mistake, and you're like, yeah, I don't at all see how the exchange argument works. Then you can at least say, and then we do some exchange, and so after I plus 1 step. So I'm going to warn the marker to watch for this, but you can at least try. A Superwitt without the Z. Already carved the whole sentence right behind it. Okay, sorry about that. That sounds painful. Okay, why does it? So before we take any steps, our empty subsolution can be extended to an optimal solution. So let's say that we've done. I'm just going to erase these up to say here. No, I'm not. I'm going to put the 6. Yeah, those 2 are still going to be the same. And we're going to do this with the 6. Okay. Oh, this is actually easier with a finger. I hope this stuff is not toxic. Okay. So let's say we had 7, we don't have 9. 2, 4, we don't have 6 and 8 yet. I can do that with the eraser at least minimizing my exposure to. 3 we've got, but not 5 and 7. 1 and 2 we've got, but we haven't got 4. And 3 we haven't got. Okay, so let's suppose that up to before we take any steps, our empty subsolution can be extended to an optimal solution. After we've taken I step, assume that after we've taken I steps, our subsolution can be extended to an optimal solution S. Okay, so there is a way to fill in the rest of this stuff such that we get an optimal solution with a minimum number of subsequences, of increasing subsequences. We show that after I plus, so you do this exchange argument, after I plus 1 steps, you can, our subsolution can be extended to an optimal solution as prime. So let's suppose that we're looking at the 6. So up to here, we haven't made any mistakes. But so we're going to put the 6 after the 4, right? Oh, right. So I should just write this down. I don't think, like, this is not in the book, and nobody teaches it usually, I think. It just came up in something I was doing, and I can use it because in dynamic programming, we're going to see finding the longest increasing subsequence. That is a classic problem. And so I think last year I managed to fool people by putting this on the assignment, and they all had it driven into their heads that you do problems about longest increasing subsequences with greedy algorithms. And then I turned around and taught them the dynamic programming, and people got confused and didn't know what to do on the exam. So, somebody's waiting. So it's nice because as I told you at the beginning of the course, don't just pattern match. Don't just think, ooh, this is an increasing subsequence problem. We're going to do this with greedy. You actually, like, algorithms is not that easy. If it were, I probably wouldn't have a job. Maybe. I mean, I'm a researcher, but if it were that easy, I probably wouldn't have a job as a researcher either. Okay, so let's suppose we put the 6 here, okay? But let's suppose S, this optimal solution that extends our solution, let's suppose S was blue, right? S puts the 6 here, okay? And we think, oh, okay, so now S doesn't extend, we put the S here. So I'm going to write that in green. But we put it here, S puts it here. And we think, oh, so now S doesn't extend our solution anymore. Well, what can we do? So let's think about this. Then you have to, the rest of S puts some stuff here. And maybe S starts some other chains here. Okay. And S is going to put, so we put the 6 here, but S is going to put some other stuff here. Okay. And then it's going to put some stuff after the 6. And maybe it's going to put some stuff after the 7. Okay. So let's call this A, and well, actually, we're not going to move to that one. So let's ignore it. So what are we going to do? Let's call this A, and let's call this part B. Okay. So, actually, let's call all of this one. We're going to leave the rest of S's solution alone, but we're going to switch A and B. Okay? So that is going to put the 6 after the 4, which is where we want it, where we put it. And why can we do that? Well, we put the 6 after the 4, and the rest of everything we're going to leave alone, okay? And so it's S's solution, and so it was optimal. So why can we do this switch? Well, 6 goes before, 6 is larger than 4. Otherwise, we couldn't have put the 6 here. So whatever element we're considering, 6, it has to be, we're putting it after the largest thing that we can put it after. So S had to put it either as its own chain, or it had to put it after something smaller. So we can move the 6 here. So we can swap B here. Why can we swap A to after the 3? Well, we put the 6 after the largest thing we could put it after, which means that whatever S put it after, either it's its own chain, in which case A can always become its own chain, or if it put it after something else, it had to be smaller. So 3 is smaller than 4. So if this is, for example, 8 or something, it has to be larger than 4, and 4 is larger than 3. So this is larger than 3. So we can actually put we can put A after here. So we can swap A and B. And that is not going to increase the number of chains, because we're just swapping something. If B is its own chain, we're swapping B to A, and A is becoming its own chain. We're not changing the number of chains, so we're going to get a solution which has the same number of chains as S, so it's also optimal, and it's putting the 6 where we want it. Okay, so after I plus 1 steps, our sub-solution can be extended to an optimal solution S. Therefore, by induction, we obtain an optimal solution. Okay? Questions? Everybody good? Anybody still there? Nobody's in the waiting room? Okay. Now, I don't know, people like last year or the year before, they found this really tricky, probably because I put it on an assignment without teaching it to them. Okay, so now vertex cover on trees and a little bit on graphs. So I don't know if we have time for the bit on graphs. Okay, vertex cover. To remember what a vertex cover is, remember this phrase, it's a vertex cover of the edges. Okay, so if you have a graph, you have some graph, a vertex cover is a subset of, so vertex cover, you should write this down. A vertex cover of a graph G is, okay, G equals, it's a pair, the vertex set and the edge set is a subset of V, subset, let's say S, subset S of V, such that for every edge in the edge set, one of the endpoints of E is in S. Okay, at least one of the endpoints. So A, B, C, D, E, F, G. Does somebody want to pick a vertex for this graph? Anybody there? A. Okay. People like starting with A. Okay. A. Somebody else want to choose E. Now notice A covers this edge and this edge. E covers this edge, this edge, this edge, and this edge. So I'm just gonna slash. So somebody else choose another one. C. Covers that and that. And another one, D. Well, actually, okay, so I'm gonna, D doesn't cover anything now, but probably you wrote D at the same time as somebody wrote C. So starting now write the next vertex you want to take, F. So actually it doesn't matter because both of these will cover this and then we're done. Okay. So F. Okay, so this graph has vertex cover of size 4. Does it have a vertex cover of size 3? I can't see one offhand. No, I don't think so. No, I don't think so. So you need one of these two. You need one of these two. You need one of these two at least. Yeah, if you take this one, then yeah, okay. So I don't think it has a vertex cover of size 3. We don't need F. We do need F because we need either F or G to cover the edge FG. One of the endpoints at every edge. So if you look at the red vertices, all of the edges have some endpoint. I mean, this one has both endpoints are in the vertex cover, but all of the others they have, and this one has both endpoints, but so yeah, this is at least. So it's one, or I can have both. Okay, so vertex cover is one of these nasty hard problems that we don't know how to do. Okay, super easy to explain. And people have been trying to solve this. We can do it. I mean, obviously we can do it. It just, we don't know how to do it in polynomial time. Okay, nobody has ever found a polynomial time algorithm for finding the smallest vertex cover. So if somebody gives you a graph and says, is there a vertex cover of size K? We don't know how to do that. In time polynomial in the size of the graph. Okay, so that's kind of frustrating, but there are, so this is going to, so I want the next bit I'm going to tell you. Can you explain that again? If somebody gives you a graph and says, and a number K, so they give you a graph on 10,000 vertices, and they say, is there a vertex cover of size 2,000? So you're allowed to choose up to 2,000 vertices out of these 10,000 vertices and try to cover every edge. We don't know how to do that. So given a graph and given a number, we don't know if we don't have a polynomial time algorithm that lets us tell if there is a vertex cover of at most that of that size. So a vertex cover is you can always add extra things to the vertex cover. So you can always say it's size K, exactly K, because you can always just add stuff if you want. We don't know how to do that. Okay. So what we can do is some instances. For example, trees. We can do this on trees. We can find a minimal vertex cover. Sorry, not minimal. Minimum vertex cover on a tree, a finite tree, let's say. If the tree is infinite, then some stuff is going to be a bit weird. But let's say finite tree. Okay. So I'm not sure I'm going to get to. You can do. There is an approximation. There are better approximation algorithms, but there is an easy approximation algorithm for graphs that I'm not going to show you today. But we can show, we don't know how to get a smallest vertex cover on a graph, but we do know how to get a vertex cover that's at most twice the size of the smallest vertex cover. And I will either cover it today or I will cover it when we get to NP complete algorithm, NP complete problems. Okay, so let's build a tree. Okay, this is a tree. Okay, so I mean at least one of them. Yeah. Yes, it has to have at least one of the endpoints. Okay, so you would think when I say there is a greedy algorithm for doing this, you would think what's the obvious way to process the vertices, right? What's the greedy way to do this? You're trying to cover the edges with the vertices. I think there's an obvious thing to do. Well, how do you sort the vertices? Right? You're going to have to consider the vertices in some order, and then you're either going to take them and put them in your vertex cover, or you're going to throw them away. That is the obvious thing you would do. That is not how the algorithm works. Okay? Which makes me think I should have saved this up for the exam or something. But no, I'm actually going to tell you this. Yes, like that is the thing that you would think you would do, but you don't. Instead, you actually start with a leaf, which is the thing with the smallest degree. Okay, it's only got degree 1. You do not take the leaf. You take the other end of the edge. Okay, so we're going to take this leaf, and then we're going to take this vertex. Okay, and now we're going to ignore. We're going to draw that. Okay, we're going to draw this in green, in blue, and this is good because my blue is kind of faded. So, and actually we're going to draw this edge in blue too, because we've covered this edge. So now, we don't have to cover this edge, we don't have to cover this edge. So now we're just considering the stuff that's left in black. Okay, so now we find another leaf. We find this leaf. We do not take the leaf, we take the other end. We find a leaf. Let's say we take this leaf. We do not take the leaf, we take the other end. We find a leaf. Let's say we go up here. We do not take the leaf, we take the other end. And we've covered these 3 edges. Blah, blah, blah. Okay, we do not take the leaf, we take the other end. Okay. And so on and so on. So now we find the leaf. Okay, which leaf do we want? Let's say we take this leaf. This wasn't a leaf before, but it is now. So we take this leaf. We do not take this leaf. We take the other end. We take this, and we get all of the vertices. Ha ha. We get all of it. We cover all of the edges. We're done. Okay. So our vertex cover is that we end up with is 1, 2, 3, 4, 5, 6. Okay, and I claim that that's the smallest possible for the smallest vertex cover possible for this tree. Okay, why? What's the magic words? Not please in this case. Why do we know that this algorithm is going to produce a smallest vertex cover? And I'm concerned that this is We have 1 minute and 42 seconds before. I'm just going to make sure that the small camera is recording because it's vital today, because we're probably not going to get a decent recording on a Zoom. Is it log of vertices? No. No, because for example, if the tree is a path, you have to do every other vertex. So that's actually half. Yes! Before we do anything, before we take any steps, our empty subsolution can be extended to an optimal solution. So before we have processed, before we have considered any vertices, now this is an interesting case of a greedy algorithm, because you start, you sort the vertices by degree and you consider the leaves first. But notice that after you take stuff off, after you pull the leaves off, something that was not a leaf before can become a leaf. I feel like we're in a cult. I have never thought of it that way. Okay, so that means that you have to resort, right? So once I've pulled this leaf off and this leaf off, sorry, once I pulled, where was it? Yeah, once you pull this off and this off, this becomes a leaf. Okay, so you have to resort. So let's suppose that after some number of steps, which we're gonna do. So before we take any steps, okay. So we're going to go back and I'm going to put this in black. Let's leave, this is blue, this is blue. So this is, I forget the order I did this, but okay. So this is not there. This is blue and this is blue. Okay, so we've done some number of steps and we've done I steps, and after I steps, our subsolution, not exactly, this is easy for trees. It's not, okay, so after I steps, we assume that we've discarded the blue vertices, making these blue now. And we've added the red vertices to our vertex cover. And there is some way to process the rest of the tree such that we get a minimum vertex cover. So our subsolution can be extended to an optimal solution. But now what do? We take, let's say, yeah, I think we considered this leaf next. And we took this vertex. So we took this vertex. Now suppose that we make this decision, but our subsolution can be extended to an optimal solution S, but S takes this one. So no, we were green and S was blue. Okay, so S is going to take this. That's blue. Not sure you can see that, but it's blue. Now we have to say, oh, S does something else at the I step. We consider some vertex, we consider this vertex, and we take this one. But S doesn't take this one, it takes this one. Well, what can we argue? How can we argue that when we take this one, it can still be extended to an optimal solution? Well, we take the green one. This is a leaf. So okay, maybe it's not a leaf, and maybe it didn't start as a leaf, but all of the other edges that were incident to it are already covered. So we don't have to worry about that. So this is a leaf, so it's only covering this edge. When S takes this leaf, it's only covering this edge. When we take this vertex, it's covering this edge and possibly some other stuff. So suppose that this is looking purple because it had some red there, but it's blue. I'm going to use a different blue. Is this a stronger or weaker blue? It's just a different blue. Okay, so let's suppose that, so S would have to take this one in order to cover this edge if it didn't take that. So let's suppose that the blue stuff, apart from the blue stuff, is the rest of S. So S took the red stuff, and then it took the blue stuff, and we took this green one. We took the red, and on the I+4 step, we take the green one. Well, notice that this one is just covering this edge. This one is covering this edge and possibly some other stuff. So the rest of S's solution is compatible with the green one, with not taking this and taking this, because all that changes is which endpoint of this edge we're covering. So with S's solution, without the green, we had to take this to cover this edge. Actually, we would also have to take this because, okay, so maybe we're going to take that as well. But if we move sort of the marker from the leaf to what was the green, then we'll be covering some edges twice, but that's allowed. Okay, it's not a problem that we cover edges twice. We just have to cover everything at least once. So we can do this switch, this exchange, and then so we're going to uncolor that, color that. It's still compatible with the rest of S's solution. So we haven't increased the number of vertices we're taking. It took this, we take this. That's both one vertex in either case. Our solution is now compatible with the rest of S's solution. We're still covering everything that S was covering. So our sub-solution after I+1 steps can be extended to an optimal solution S prime. Therefore, by induction, we get an optimal solution. Okay. Because of time, I forgot to reset this. No. Okay, I'm going to assume that 5 minutes passed. Well, 6 minutes, but that's okay. So I'm going to skip the argument for why you can do. I wanted to show you the approximation algorithm on graphs because it's a hard problem. So when you're faced with one of these hard problems that we don't know how to do, one thing you can do is say, oh, well, maybe you can actually just do it in practice. Like maybe it's not really that hard in real life. It's only hard on these orchestrated, really pathological instances. And so you can just try it. And you won't have good bounds, but maybe it works okay in practice. The other thing you can do is say, well, maybe the general problem is hard, but I'm not working on the general problem. I'm working on trees. I'm working on planar graphs. So a lot of stuff is hard for planar graphs. A lot of stuff that's hard on general graphs is also hard on planar graphs, but sometimes it's a bit easier on planar graphs. For example, coloring, it's still hard, but it's not as hard, we think. But sometimes some stuff is actually easy on planar graphs, and a lot of stuff is easy on trees. And actually, as somebody said, somebody mentioned dynamic programming. You can usually use dynamic programming to do stuff on trees. We're just doing greedy at the moment. The other thing you can do is say, well, I don't think I can get an optimal solution, but maybe I can get a solution that's really close to optimal. So if I get finished with knapsack, I'm going to show you how you get a solution that's at most a vertex cover that's at most twice as big as the minimum. Okay, but first knapsack. Oh, so I'm going to have to. Everybody has access to the scribe notes from last year when I made the students last year actually write what I was saying. Okay, so this is, but it wasn't just that I was being cruel. Last year, it was the first time anyone was dealing with online teaching. Well, I mean, some people have been doing this for years, but first time I had been trying to do this. So I didn't know how to do a midterm. So I gave people the option of not doing a midterm and writing scribe notes instead. So it just wasn't just sort of random cruelty. And there's a really cute picture of knapsack in the scribe notes from last year, which I may steal for the lecture notes this year. So knapsack, you imagine you have a knapsack, a backpack, and it has some capacity. So knapsack with some capacity C, and then you have some food items, for example, well, some items. And since this class, I had breakfast, but that was a while ago, and it's lunchtime, so let's talk about food. Some food items. Oh, now I'm going to be really hungry. So I have like nothing in my fridge, but suppose I have some cheese. So you have cheese, you have bread, you have an apple. What else can you have? Cheeseburger. Carrots. I actually have carrots. I have. Oh, so actually, I'm going to leave out eggs. Kool-Aid. Yeah, this is going to be an interesting one. But let's suppose that you have you have lots of different sizes of containers, so you can choose however much Kool-Aid you want to take. Wasn't in there too long. Yeah, it's hot today. It's like it said it's going up to 24. Okay, so you have some items. Each one has, so for this problem, we're going to assume that, I'm just checking, nobody's trying to join. You're going to have some weight. And then you have some benefit. So let's say you have calories. Like how much we like it, the flavor, whatever. Okay, so let's say the cheese, you have 1 kilo of cheese. And 1 kilo, I have no idea how many calories 1 kilo of cheese has, probably a lot. So let's say it's 1,000 calories. And let's say you have 500 grams of bread, but this only has 100 calories. You have an apple, this is maybe 100 grams, big apple, and it has 50 calories. Okay, cheeseburger, let's say quarter pounder would be like 125 grams ish, and this is also going to be 1,000 calories. Okay, carrots, you have 1 kilo of carrots, and but this is only 200 calories. Kool-Aid, let's suppose it's frozen Kool-Aid, 9,000. Okay, 9,000. So okay, let's forget about. I don't know how to deal with the Kool-Aid at the moment. I have a thermos. Let's think of the Kool-Aid supplement. Okay, so your knapsack, some capacity, let's say you can take, it's a very small knapsack. You can only take 1.5 kilograms. It's like a lunch bag, okay? So you want to take food, it's gonna be a long hike. You want to take the maximum number of calories you can without going over the capacity of your knapsack. And here's the important thing for this problem. You can cut these items, okay? So you can't go over the capacity of the knapsack, but if you get up to the top of the knapsack and be like, oh, well, I have a kilo of cheese, but I can only fit 200 grams worth in, then you can cut and just put in 200 grams worth of cheese. So maybe if you get to the top and you're like, I can only take 70 grams of cheeseburger, you can cut the cheeseburger. This is why the Kool-Aid is a problem. Not sure how you cut the Kool-Aid. You can like chop the apple up, you can like chop the carrots. Okay, so how are we going to do this? How do you decide what to take, how much stuff to take, so that you optimize your the calories in your knapsack? Now I'm so hungry. Right, you take the caloric density. Right? So what are we going to take? I think it's going to be the cheeseburger. This is not the optimal way of actually putting it in the knapsack. We're going to put the cheeseburger at the bottom. So the cheeseburger goes here. It's a very rectangular cheeseburger. So now we have a little less than, like, we have 1,375 grams left. And we took the whole cheeseburger, okay? Full of burger and wheat. Yeah, but we only have one cheeseburger. Yeah, somebody has, some health nut has been free has had access to our refrigerator and thrown away everything. We just managed to hide the one cheeseburger. So so we only have one burger. So now what are we going to take? So we would actually have to think, this is, so the next best, I think, is to take a kilo of cheese. That doesn't, healthy people would maybe, I don't know. So we're going to take a kilo of cheese. So 1 kilogram of cheese. This is actually the kind of stuff I tend to take on my hikes. That's okay. So this, now we have 375 grams left, because this is 1 gram for 1 calorie. This is 1 gram has way more than 1 calorie. So the cheeseburger is best. Then this is 1 to 1. This is 5 to 1. This is 2 to 1. And this is 1 to 5 to 1. So we could take the carrots, or we could take the bread. It doesn't matter if you take the carrot, but you can only take 375. So let's say you take, oh, let's say that this was 150, so that we're going to take the bread. So we're actually going to take a cheeseburger and cheeseburger ingredients. So this is actually way too. So this is the 375. So we're going to take 375 grams of bread. Okay. So why is this? When we take the apple next, the apple is Oh, right, sorry, because this is 5-to-1 and this is 2-to-1. Yes, you're right, sorry. We would take the apple. Because this has the next highest ratio. I was getting confused. And then we have 275 left, and we're going to take 275 grams of bread. So down to about here, it looks like a healthy knapsack. And then you think, oh, maybe like this and an apple and 200 grams of cheese. And then you realize, no, it's a whole kilo of cheese with a cheeseburger buried under it. So from above, it looks good. And then when you get down into the height, you actually have the calories. Okay. So we don't have very much time. So I better stop joking around and actually get, why is this the best we can do? Well, before we take any steps, we have this empty knapsack. Our empty solution can be extended to an optimal solution. Let's suppose, how did I do that before? Okay, so I had like our partial solution. So we have taken some items and maybe we cut them, or well, we don't cut them until they don't fit. But we've taken some stuff, and then we're processing these in order by density, and we take something, and let's say that we take this. So before we take any steps, our empty subsolution can be extended to an optimal solution. Suppose that after I steps, our subsolution can be extended to an optimal solution S. So we take the green thing, and let's say that this is S, this is us, and this is S. So S takes the same two things to begin with, but then it decides not to take the green thing. It takes, or maybe it takes a little bit of the green thing, but not all of it. And then maybe it takes some blue thing. Okay. Well, let's just suppose it takes some blue thing. We'll call it the blue thing. The blue thing could also be, let's make the blue thing bigger. Let's make the blue thing two blue things. So if we're looking at S's solution, you've got this. Okay. So how do we do the exchange? Well, we're going to take this, which S didn't take, and let's say that this is 100 grams. And now we're going to take, so this blue thing could be 100 and 200 grams. We're not going to throw all, and then it's got some other stuff on top. Okay, I'm going to actually use the new blue marker because it's desperate times. It's got some other stuff on top. So what are we going to do? We're going to take the 100 grams of this, and we're going to cut. So this is why we need this argument that we can cut. We're going to cut this blue stuff away. And we're going to stick in here the 100 grams of the green thing. Okay? So we leave the rest of it alone. So all we've done is taken 100 grams of whatever this was, thrown that away, and inserted the green thing. Okay. Why do we know that that doesn't reduce the overall caloric load of S's knapsack? Well, because we sorted these things by density. So that means that this 100 grams that we inserted here, it's got more calories than the 100 grams of blue stuff that we got rid of to be able to insert it. Okay, because it's at least as calorically dense as the 100 grams of whatever was in here. And we know that we can get exactly 100 grams because we can cut the blue thing to be able to fit it in exactly. Okay, so now we take S, we do this exchange, we like exchange an apple for the bread, we like cut the bread in, like cut an apple shape out of the bread, and we put the apple into the hole in the bread, and then we have not decreased the caloric load, so we get this solution S prime, which now extends our subsolution after I plus 1 steps. Okay. We have 4 minutes. So this does not work with, for example, eggs, a jar of pickles, you know, other stuff that you cannot cut, right? Because if you think, suppose that you have an egg. You cannot cut an egg, an uncooked egg. So maybe an egg is the calorically densest thing. So an egg is what, like 20 grams? And it's, I don't know how many calories, 100 calories. I don't usually pay attention to calories. So it's 100 calories, say, and then, so then you have something which is the whole 1.5 kilos of, I don't know, what's something else we can't cut? 80 calories. Are people looking this up, or do you just know this? I was close. Maybe it's a big egg. So what's something else you can't cut? You can cut a watermelon, but then it will go bad. So let's suppose you have a watermelon and you don't want to cut it. And it's 1.5 kilos, and it's 1,000 calories. Okay. So, and this is the only stuff you've got. A container would cut some it. What, a bottle? Yeah, as I said, a bottle of pickles or something. No, that's okay. Okay, we're just going to keep going because I think the little camera will have some time left. It has like 3 minutes left. So in 3 minutes, we're going to stop because we're also out of time in 2 minutes. So, okay, if you do this and you say, oh, well, we're going to do this by density. This is the most dense. So you put in the egg. And then that's kind of a, it should be more oh boy, but okay. And then because you put the egg in, you don't have room for the watermelon. So the sorting thing doesn't work in the case of binary. So when you're allowed to cut, it's called fractional because you can take a fraction of the thing. And when you can't cut the stuff, it's called binary. You can also get, I'm not going to have time to do it, but you can also get an approximation algorithm, a greedy approximation algorithm for the binary case, but not doing it by density. Maybe I'll put this on the assignment. But the approximation ratio, again, you can get 2. So you can't get the maximum number of calories, but you can get at least half. Remember, with vertex cover, you couldn't get the minimum, but you could get twice the minimum. Here, you can't get the maximum, but you can get at least half. but not sorting by this way, because this way you take if you sort by, I mean, you can sort by various things, and we actually don't, there isn't a greedy algorithm for doing this. And as we'll see after the midterm next week, when we get into dynamic programming, I'm going to teach you a dynamic programming algorithm for this problem, but it looks like it's polynomial. But remember that stuff about factoring, where you said, oh, well, you can find the factors in linear time. If I give you n, then you can find the factors of n in time O of n. Well, the same thing. You can find the dynamic programming for knapsack, dynamic programming algorithm for knapsack runs in time that's polynomial in the size of the knapsack. But the size of the knapsack, I give you the size of the knapsack, the statement of the instance. I don't write the size of the knapsack in unary, I write it in binary. So actually, this problem, binary knapsack is NP hard, but it's NP hard in the weak sense, which means that if I give you the instance with all the numbers written in unary, then you can do it in polynomial time in the amount of paper I needed to write that. But if I give it to you with the numbers written in binary or decimal or something, then we don't have a polynomial time algorithm for it. That problem, knapsack, yeah. I always get like, so there's knapsack and substance. I think this one, I think, yeah, when you can, I'm pretty sure this one is knapsack. It would be naturally called knapsack. There are versions where you can take multiple instances of stuff. I think this is, I'm pretty sure. I'm thinking about food. Oh, so now we've lost the little camera. We're also 2 minutes over time, so I'm going to call an end to this class. Good luck on the midterm. I'm going to make an announcement. No class next week. I'm sorry I'm behind on the lecture notes and the assignment solutions and posting assignment 4 and basically everything. But the talk went fairly well yesterday. I don't have another invited talk until July, fortunately. So any questions? I'm not going to, I could post the video. It was a very dense talk. A question about the midterm? Yes, what about the midterm? Will it be open on Monday and end on Friday? Yes. I'm going to have to be careful with the rules because, so I'm still recording here, but it's not on the, because last year, so I was kind of impressed by the nerve of this student. I told people it's open book and you can look for information on the internet, but you're not allowed to ask people. Which lectures should we review? Everything. All of E. So I told people, look on, but you're not allowed to just get people to do your work for you, but you can check the internet. And so apparently somebody interpreted, either they ignored me or they interpreted that to mean you can post the midterm questions on Stack Exchange. Because I saw one of my midterm, was it an assignment question or was it a midterm question? I'm not sure. But they were saying, I don't know how to do this. And so it was anonymous, so I didn't know who. But so I went in and said, well, I gave them a hint. I answered the question and I signed it as me. So they could see, and it was obviously somebody from my class. So they could see that it was the instructor answering their question, which I thought would freak them out. And they would just disappear, but they came back and asked for more details. So, and so we had a little discussion about, like, is this actually allowed? Not between me and the student, but between me and sort of other faculty people. And I decided that I should say it was allowed. I'm not going to allow it this year, but I decided that I would allow it last year because I couldn't think of anything I could do to stop it. But please don't actually ask for people to give you the answers on Stack Exchange, because the final exam is going to get proctored by the faculty, and they will like all kinds of, so you actually really, no, you can't ask. I mean, please don't, because you should actually learn this. The questions are not that hard. I mean, they are hard, but they are hard in sort of a teachable moment way. It will make you think. Stack Overflow. One of them is just for like theoretical computer science, and Stack Overflow is we can't collaborate like on the assignments. I haven't decided that yet. You can't work in groups. Like you have to turn in your own midterm. I don't know. I think no, don't collaborate. What I'm going to do once I have the Stack Overflow is part of Stack Exchange. Okay. Once I have the exam written, I'm going to do what I can post the exams from previous years so that you can look at those. Once I have the exam written, I'm going to usually I show it to some of the other professors, and sometimes they say, "Oh no, way too hard," and then sometimes they say, "No, that's fun." So if they say it's way too hard, then maybe I'll allow collaboration. Not like you have to understand the same rule applies. You have to be able to explain your answer to me. Always. I can challenge you. And if you don't know where the answer came from, then there's a problem. I don't know. I'll have to think about this. You need to be able to explain means yes. So that's the rule for the assignments. For the midterm, maybe it's best you don't collaborate, because for the final, you don't get to collaborate. Okay, good luck. It's not, so I think I know what the questions are going to be, and it's not that bad. I haven't figured out, I have to have one more question about greedy algorithms, and I haven't figured out that out. Okay, so we are way over time. I'm going to stop the recording. Good luck. As I said, I'm going to make an announcement, no classes next week. So see you in like not quite 2 weeks. Okay. Ciao. Oh, the final stresses the cause. We have to pass the final in the rest of the class. Okay. Yeah. Ciao. Stopping recording now.